Okay, so let's come back. So in the past hour, we talked about the idea of dynamical programming, and actually we talked about this specific example of weighted interval scheduling. So for this problem, we have some thoughts here. So in general, we were talking about this strategy. In general, the optimal strategy, it either has the job J here or it doesn't. Nevertheless, from the two cases, we can result in a specific recurrence relationship here that basically OPTJ, equals the maximum of Vj plus OPT Pj of, and also on the other hand, OPTJ minus one here. So one issue we notice, using like a very brute force way to run this on recurrence is that we are actually, this is very repetitive. Actually in general, the cost of the recurrence can even be exponential time. So this is definitely not something we want. And actually a very easy way to solve this is actually by memorization. In general, for all such kind of dynamical programming algorithms, instead of just brute force writing down recurrence, you can always have a table. You have like a storing table here. For this algorithm that we have been written down here, you can initialize an empty table. Originally all the entries are empty. Of course, M0 is going to be 0. But as long as, in this kind of recurrence, as long as one of the entries, it is empty, it is empty, it is the case that you should really compute that. This is the place where you call the recurrence relationship, and you compute the corresponding MJ here. But actually, on the other hand, if it is not empty, if it is already computed, you just return that. You don't need like any further recurrence accordingly. So this is basically like a memorization version of this dynamic programming. So is there any question of this error? Okay, so I guess this should be a relatively transparent. Basically, this memorization algorithm can address this. We call this recurrence for in the worst case exponential times. So now let's analyze the running time of this algorithm. So the running time, maybe let's go to the next page. Running time. So claim. So the memoized version of the algorithm, it actually takes O n log n time. So why is this the case? So basically for running this algorithm, the very first step here, we basically need to sort all the jobs. So basically we sort by finishing times. And this causes O n log n. And the second step is that basically we need to compute all the p's. So basically this cost is also O n log n. So why is this the case? So there are actually n entries of all the p's. From P1, P2 until Pn. So we say that computing each Pj takes O log n cost after we have the sorting. F1 are smaller than F2 are smaller than F1. So why is this the case? So we just take another look at basically what is the value of Pj here. So basically for the value of Pj here, we need to have this relationship. So basically Fpj should be smaller than Sj here. And also on the other hand, we know that the Pj plus 1 interval is actually not compatible with the jth interval. So we just know that this is actually smaller than Fpj plus 1. So we actually have this ordering. P1 is smaller than P2 is smaller than P, etc. So why this cost? For each this PI, we can actually each Pj can be computed in O log n time. Just check the position of Sj among the sequence. Among this sequence. F1 or F2 until Fn by binary search. Because we know that this is ascending sequence, and we know that we must have this relationship that actually according to, let's just write down this again, according to fpj smaller than sj are smaller than fpj plus 1. So you just check the position of sj in this sequence. I mean, maybe for instance, is sj larger than fn over 2 or not? I mean, let me further write on this. It's actually or not. If true is f3n over 4 smaller than sj or not. If false is fn over 3 are smaller than sj or not, etc. This is a very standard binary search, and it is very straightforward to see that basically a cost of this is going to basically, for computing each of the pj here is basically going to give you a log n cost. After you're having run the first step, you sort all this value of the f's. So any question for this one? Okay, so that is basically saying, I mean, the initialization, I mean, for this algorithm, for this interval, weighted interval scheduling problem is going to cost O n log n here. So basically for both the sort and compute step, it is basically going to take this cost. So what is actually remain here? I mean, initialization of the M table is just trivial. I mean, it's O1 cost, but all the entries are actually, I mean, this is not a big deal. So the remaining thing is that we need to have a good understanding about what is the cost of this function. So this M compute object OPT here. So basically, we need to understand this. So basically, we need to have a good understanding for that. So basically, each call of it actually takes one time. I mean, this is a relatively straightforward because inside each calls, I mean, you just have in the case where mj is empty. I mean, it's just you compute a maximum of 2 values. So this is relatively straightforward. I mean, this is just it's going to give you like a O1 time cost and actually add actually returns existing value mj, or it actually fills in one new entry mj and makes 2 recursive calls. Right. So we can actually have, I mean, basically, as long as we have like an empty entry, I mean, we have an empty entry here, we are going to call the recursion here. I mean, this seems like the most complicated place we're actually calling this. So I think maybe it makes sense that we consider such kind of measure. So we call this a progress measure. Let's call this like a phi here to be the number of non-empty entries. Excuse me. Number of non-empty entries of this array M. So initially, of course, phi equals to 0, and throughout, phi is actually must be smaller than. I mean, even if we compute OPTN here, it might happen that some of the values in the middle is empty, but this is not so important. We know that, of course, according to this definition, phi is at most n here. So we know that basically, I mean, for this for the second case, I mean, fusing one new entry of the M's and make 2 recursive calls. I mean, only in this case, I mean, we are actually actually for the second case here, we are going to increase phi by 1, and actually, and this is going to make 2 recursive calls. So this just implies that in total we have at most 2n recursive calls. So this is a main place that is, the difference between the memorization algorithm and the brute force algorithm. Because we have an entry here, and basically we update the corresponding entry according to whether we have an empty entry or not. So basically, it makes a lot of sense that then we consider this kind of value of 5 here, and basically we want to have a good understanding about what is the number of non-empty entries of the M's here. And actually, according to this, we can have recursive calls, but we have the recursive calls only if the sum of the entry is empty, and we need to fill this with some of the recursive calls. And basically, as long as we have a recursive calls, it only happens in the case, basically the second case. In this case, we increase the value of 5 by 1, we make 2 recursive calls. And basically, we know the value of 5 should be at most n throughout. We basically have the conclusion that at most 2 recursive calls. And basically, it is quite straightforward. In each recursive call, you just compute the maximum of 2 values, and this causes O of 1 here. And this just suggests that the overall running time of M compute a PTJ is big O of n here. Since we have only at most 2 iterations, and each iteration takes O1 cost. So overall, the whole algorithm takes cost O(n) log n. Or we can actually further make a remark if all the Fi's are pre-sorted and Pj's computed previously, the cost of dynamic programming is only O(n). It's the only part of if we run this M computer PTJ here. Okay, nevertheless, the overall cost is O(n) log n. Okay, so any question about this time cost analysis?
Why not just use a for loop instead of the?
Right. That's a good point. Because I think this is the intuition. We want to introduce the dynamic programming. Actually, I'm going to introduce in a minute. The intuition of dynamic programming. It's just in general we have maybe a difficult problem, and we want to look at take a close look at the problem. What is the optimal solution? It got to have some structure we are going to satisfy, and we consider maybe we want to basically we can make this a smaller problem, but making this a smaller problem is typically like a recurrence relation. But actually for this specific problem, I think one of the students is actually making a very good point. This does not have to be a recursive. We can actually give a better algorithm for this. I won't say it's a better algorithm, sorry, but at least we can consider, maybe like an algorithm that does not have any recursion. So how do we actually do that? Actually, this is a good observation. So we can actually unwind our recursion. So unwind is just somehow, this is, you can probably use it in English word that maybe you will just remove the recursion, but somehow unwind is that basically you're motivated from this, and you can tweak the structure of the algorithm that you get rid of the recursion, but somehow this is still motivated by the original dynamic programming algorithm. So by doing this unwind recursion, you just, the main point that we are actually going to switch is that we can actually go from top down. This recursion, it is really like a top down because we have a large problem. You go down to smaller cases, but actually you can unwind the recursion by going from top down to bottom up. So how can we actually do this? So we can actually call this like an iterative compute OPT. So how does the current algorithm work then? So we consider this as to be M0 equals to 0. And actually, as the student suggests, we can actually just use a for loop. For j equals to 1 to n, we just compute mj to be the max pj plus mpj j minus 1. So clearly, this is an algorithm that does not have like a recursion anymore. It is iterative though, because if you want to currently compute the value of mj here, it suffices that, I mean, you call the previous values. I mean, according to this recursion, I mean, when you compute the value of mj, you should have already have the value of m0 or m1 until mj minus 1. And basically, you know that is true because the mpj, it actually belongs to m0, m1 until mj minus 1. So you know that, and actually for the second value mj minus 1, you just computed in the previous one. So you just basically use the for loop here, and you can actually just build up this array from left to right, basically fulfill all the values here. So this is actually a very good point. Actually, for a lot of dynamic programming algorithm, you can just consider like a very similar strategy. You just like a little bit tweak the structure. I mean, in general, maybe you think about optimal solution for a large problem. This is really like a top-down kind of thing. But in general, you can break up the recursion. I mean, or I think more precisely unwind the recursion by actually, instead of using this kind of top-down strategy, you can write this corresponding bottom-up version. So this is actually a point that I'm introducing. So any further question? So this is actually a very good point that we can unwind the recursion here. So another point that I would like to emphasize, so if you didn't notice, is that basically for this algorithm, I mean, for this minimization version algorithm, we actually return the corresponding value of the maximum. I mean, it's just return the value, but maybe, I mean, for instance, if this is really like a scheduling problem that you're going to take place, I mean, in real problems, you probably not only want to have this, I mean, what is the maximum value, but it's actually a solution for that. I mean, what are those intervals that you're actually going to pick? So this can also be finished by a relatively easy fix like this. So we consider an algorithm like this. So the first step, I mean, of course, we can just use the unwind version, recursion version, but let's just continue with maybe, for instance, the original recursive version. So M compute. We just run this, and basically we store the values of the M matrices. So we can call an algorithm like this. So we run an algorithm which is called find a solution. Find a solution n. So what is this? So basically for find solution j. So if j equals to 0, we of course in this case OPT is 0, and we don't have any interval to choose. We just output nothing. Else if, I mean, let's just think about, I mean, what is actually going to happen here, or maybe this is the unwind version, or maybe the original recursive version. So here. So basically here we are going to take the maximum of two values. So in this case, I mean, if we want to consider how basically we want to build up a solution. So basically, else if maybe for instance, we can encounter the situation that Vj plus mpj actually are larger than mj minus 1. So in this case, I mean, we just print j. Because this just means that actually picking the jth interval is helping you. It's actually better than the second case that you don't pick the jth interval and just like go to the OPT of j minus 1. So in this case, you know that it suffices that you pick the jth interval and you just print j here. And then you recursively run find the solution. Else, I mean, in the else case, it simply means that Vj plus m of pj actually smaller than or equal to mj minus 1. In that case, it suffices that you run find a solution. find, let me actually write down in the next slide. So just run, find the solution. K minus 1. So basically, it is not hard to see that using this kind of find solution, this kind of idea, you can just, according to the prints, you can just recover what is the optimal solution for this unweighted interval scheduling. Okay, so any questions? This basically finishes, the two remaining parts for unwind the recursion and also for returning the whole solution. So I think, and also the time complexity of the weighted interval scheduling. So this basically finishes this part. And I guess if I have any questions, just feel free to ask. Okay, so here I think basically we have been demonstrating an example. Basically this weighted interval scheduling problem. I think at the very beginning of this lecture, I talk about a little bit. This kind of summary English that in general for this dynamic programming problem, we want to break up a problem into a series of overlapping subproblems and build up solutions to larger and larger subproblems. So this is still a little bit vague. In general, maybe this is also currently a relatively good time to make some conclusion here. In general, maybe a little bit more detail, but still some kind of a general guideline for using the dynamic programming idea. So let's say like a basic outline of dynamic programming. So a basic guideline here is that basically we notice that they are actually only a polynomial number of subproblems. So this is very important because actually, I think here, in the time complexity analysis here, we have this kind of specific file here. That in general, we know the number of recursive calls is actually at most 2n here, or maybe even simpler. This problem can, this kind of algorithm can be actually unwinded. Using this kind of iterative idea. So this is actually a direct observation. But in general, maybe for instance, you have a problem whose dynamic programming structure is super complicated. If the number of subproblem is too large, this is not going to work. So this is actually something we need to be careful about. And actually, the second point along this is that the solution to the original problem can be easily computed to the from the solutions to subproblems. So this is actually a very important point that actually observation that we make is basically this recursion. You got to take a close look at the optimal solution that is going to have for this problem. Okay, you have this optimal solution. Maybe you want to make a discussion, maybe begin with some trivial discussion. It either chooses structure or it doesn't. But from this, you can clearly see that based on this discussion, you are actually going to have a recursion formula according to this. And actually, for this problem of weighted interval scheduling, this recursion is actually a relatively simple. In general, as long as you want to solve a problem using dynamic programming, you should satisfy that the solution to the original problem can be easily computed from the solution to subproblem. For instance, if there are like a lot of cases, also the relationship between optimal values, they are not so clear. Then you maybe want to be find like a better algorithm instead of maybe, for instance, like a better dynamic programming algorithm, or maybe others. So this is definitely something you in general you need to be careful about. So the third point is actually, it is a little bit implicit, but we can still notice is that actually there is actually a natural ordering on subproblems. From smallest to largest. and together with an easy to compute recurrence. That allows to determine the solution to a subproblem. From the solutions to some number of smaller subproblems. I mean, this is also a very important because I think in general, I mean, not only we actually we need to have such kind of recursive formula. I mean, basically, we have this kind of recursive formula, but actually implicitly we are actually having an ordering here, and actually we here the ordering we use is that basically we have the order of all the finishing time of all the intervals, and basically according to this finishing time, this gives us a very convenient way to for this problem. I mean, we have this parameter j here. I mean, we have the corresponding OPT j here, and this is actually having such kind of, I mean, an ordering from smaller problem to larger problem, and this really facilitates us to actually break up a large problem into a smaller problem and can subsequently using recursions to solve this. Okay, so I guess this is still, I mean, a little bit vague. I mean, I've been talking, I mean, in general about this kind of summary here. So let's continue to see some further examples. So we have been seeing like this weighted interval scheduling problem in this as a first example here. So let's consider maybe some other example that of also of general interest. So here, let's talk about this problem of segmented least squares. So this is some problem that is super important in statistics. So in general, let's talk about the least squared. As I mentioned, it's a fundamental problem statistics. So what is this? So for this problem, we are actually given endpoints in the plane. And that is basically x1, y1 until xn, yn. And basically, we want to find a line. Let's say y equals to ax plus b that minimizes the sum of the squared error. And this is actually the sum of the squared error. So that is basically the acronym of this sum of the squared error. And this is actually going to equal to the summation of all the data points. I mean, basically the difference of yi minus axi plus b, or basically we just write yi minus axi minus b squared. So basically, maybe let's actually draw an example here. I guess we just exactly have a spacing here. So we have like this. So we have x and we have y. So let's consider maybe, for instance, some data points like this. So for this group of data points, maybe we have this corresponding x values and y values. So we know that a corresponding line, I mean, basically a line that achieves the minimal SSE, it should probably be something like this. It should probably be something like this. And basically, this is going to probably give you a small SSE here. So this is basically like a specific way that we formulate this statistical problem, the least square problem. And in general, this is just called data fitting in general. I mean, here it is a very simplified version of data fitting problem because we want to find like a linear regression. Basically, we want to use like a linear function to approximate the data points you have. But maybe, I mean, in general, maybe this is probably not something that is so ideal. I mean, in general, maybe not all the data points are actually on a certain line. Maybe you want to consider a little bit more complicated scenarios. I mean, I mean, but in general, actually, for data fitting, I mean, or also like regression, you can have like a course for a whole semester in statistics. I mean, this is not something we are actually going to introduce. I mean, but actually, we are going to introduce some ideas. I mean, some ideas based on dynamic programming that can actually have correlations with statistics. So maybe let's begin with this least square problem. So this least square problem, I mean, you can see this problem is really actually has a very simple structure. So actually, this SSE, it is actually a quadratic function in A and B. So here you can just regard all these xi's and yi's, they are just like, I mean, parameters, but actually constant parameters. So basically, just because for finding such kind of line, y equals to ax plus b, the only two parameters that you should really care about is actually the value of a and the value of b here. So unfortunately for this SSE, actually they are in terms of a and b, they're just quadratic functions. So you can actually make some calculation and actually by taking derivatives. Derivatives in a and b. So these are just some technical details that I won't work on, but it is not hard to see that can actually the good values of a and b they can actually for a and b equals to this. So a should equals to n times the summation of x, y, yi minus the summation of xi times the summation of yi. And this is actually going to be divided by n of summation I xi squared minus the summation I xi squared. And actually, b equals to the summation of I yi minus a times the summation of xi divided by n. So this is something really standard. I mean, as a and b, they're actually quadratic functions. You just make some take the derivative, make some calculations. You can figure out that for this very direct SSE problem, these are actually the best solutions for the values of a and b here. So how about the time complexity here? So basically, we can say that the time complexity for this problem, it is actually O of n. So why is this the case? So here, the main thing you just need to compute is basically, for instance, like summation I x y yi, summation xi, summation yi, summation xi squared. I guess those are the main things that you need to compute. I mean, each of the summation is going to take you O n costs, and there are actually, for instance, 4 summations here. So the overall cost should also be O of n. Okay, so any questions for this? I mean, the SSE, I mean, for this SSE definition is current money and time complexity analysis. Okay, so if there's no question, I think maybe we want to talk about something a little bit more interesting. I mean, as I just mentioned, I guess this for this specific problem, you can directly solve this. I mean, this is a quadratic function. I mean, you just take the derivative and you can find out the exact solution of a and b's here. And in general, in statistics, people talk about like a more difficult, I mean, data fitting or regression problems. So here, maybe let's talk about, for instance, I mean, one a specific case, maybe we also encounter in real cases. So for instance, what if the points lie in roughly, say like a sequence of several line segments. So what do I mean by that? So for instance, let's maybe consider such kind of plot, xy. So instead of very nicely having like a line, roughly speaking, I mean, having points, roughly speaking, very close to one line, maybe let's consider, for instance, this case. Maybe you have points like this, and then points like this, and maybe then points like this. I mean, if you consider this case, I mean, if you only consider, I mean, one linear regression, maybe for instance, one line. Maybe for instance, I would guess that like an optimal solution is probably going to be something like this. But unfortunately, for this part, and also for this part, it's probably going to get a little bit big. If you only make a regression for this problem, only by like one linear function. But I think it is actually also a very natural strategy that in general, maybe you want to consider a sequence of several line segments that you consider. This is typically also on the other hand called piecewise linear functions. Like for instance, maybe you can consider this kind of linear function. Maybe for instance, it's going like this. I guess you can maybe consider this a piecewise linear function, and I believe that this piecewise linear function is actually going to give you a much smaller SSE compared to just using one line. So I guess this intuition should be relatively straightforward, right? So based on this, I guess we can in general consider like a problem like this. So we are actually given endpoints, in the table. We'll call them x1, y1 until xn, yn. Without loss of generality, we assume that x1 is smaller than x2, smaller than xn. It's just an ordering of all these points. We can actually find a sequence of lines minimizes fx. So this is basically a definition that we in general we want to consider here. But I guess this is still a little bit vague here. Because we want to talk about for instance different lines. For this specific figure, we can clearly see that three pieces of line should be better than just using one line. But in general, maybe for instance, maybe for this figure, you use like 100 lines. It is definitely going to be a little bit better. But not by a lot. In general, if you consider like a super complicated model, you definitely have the problem of overfitting. So you don't want to overfit a data set. So in general, a question that in general we want to consider in such kind of data fitting problem is that, maybe in general, from a high level point of perspective, we can ask what is a reasonable choice of fx to balance accuracy. And on the other hand, we call this parsimony. So accuracy is just like in terms of goodness of fit. So basically, how well we get this SSE here, and also on the other hand, parsimony here. For the specific problem of linear regression, we call this basically this is just corresponds to the number of lines. This is really, in general, maybe you think about the question here I'm writing here, like what is a reasonable choice of fx to balance accuracy and parsimony? This is really like a wide question. This is, from a high level point of perspective, we need to think about such kind of question, but we probably still need to be a little bit more focused. We definitely need to pin down a little bit more details. How we actually characterize, especially how we characterize parsimony. We definitely probably want to think about this. We probably need to pay some penalty. You don't want to use a lot of lines, to actually overfit the data. So for instance, maybe you want to pay a penalty like this. For instance, maybe we want to consider like a trade-off here. So consider a trade-off between the sum. The square errors in each segment. And the number of length L. So we consider like this. We consider the value to be E plus a C times L. So where L is the number of lines and C is basically fixed constant. I guess this is at least one way that we can think about the problem. If you want to make some trade-off, this C is basically like a penalty that we are going to pay here. If you use a lot of lines, basically the cost that is going to increase is like linearly increasing. That in general, as long as you have like L number of lines, you're going to pay a cost of C times L. And also on the other hand, you need to have a good bound, basically to bound the sum of the squared errors here. And basically you need to have a good control for that. Okay, so any questions for this definition, basically the thoughts for this? And this basically you see, I call this like a segmented least square problem. And basically, all these different segments, they're actually segmented. Why this is called a segment least square problem? So any questions for this? Okay, so if this is clear, we now have this formula that basically, we know that we are going to have a clear study about like the squared sum, the sum of the squared errors here, and actually the SSE, and also on the other hand, we plus like a C times L. So basically, the L here is the number of lines, and C is a constant. So we consider like for this, we need to consider some further notation. So basically, this notation is also to facilitate our understanding of the problem. And here we are talking about dynamic programming. So here we are actually having some definition that is actually very convenient for using the dynamic programming idea. So we call the OPT of J here to be the minimum cost. The minimum cost for points. P1, P2 until Pj. So basically, just Pi equals to Xi. So similarly, we can define like another parameter Eij here to be the minimum cost of the squares on 4 points. Pi plus 1 until Pj. So here is I think I should probably mention a little bit more. Minimum cost of squares for points by a single segment. Let me double check on this. Yes. A single segment. So basically, we need to break the problem. We need to break the problem into a few different segments. So here, at a certain point, we definitely, for instance, around this region, we are actually using this segment. Using a single segment. So in general, in terms of characterizing this optimal cost, it also makes a lot of sense that maybe you want to consider like a specific range, and maybe, for instance, between the vertices, between the points Pi plus 1 until Pj, maybe among those you actually want to use like a single segment. And actually, it is known that basically by this definition, by this discussion here, the definition of Eij for this value can be very efficiently computed, and actually the time cost is basically ON. Okay, so after having this definition of OPTJ and actually also the definition of Eij here, it is very natural that we can want to consider what is the structure of OPTJ that is actually having. For the optimal solution, after all, at last, it definitely has like a segment like this. So finally, it ultimately, of course, going to have like a segment. So let's just like say the last segment uses points. Let's say Pi or Pi plus 1 until Pj for some I. So this is the point we look at the structure of the optimal solution here. So in terms of this, we actually know that the cost is actually equals to Eij here, as we the I here is actually this I here, the last segment, basically the range it covers. So actually this equals to Eij plus C plus actually OPT I minus 1. So because here it is OPT I minus 1 because we need to think about, the last segment has already covered, the points, P1, Pi plus 1 to Pj, but we haven't finished the points, P1, P2, until Pi minus 1. So that is the reason here why we actually plus OPT I minus 1. Or in other words, how do we actually see this? So in general, it works like this. So we basically, according to this, we got a recursive relationship, OPTJ. Actually equals to 0, 0, if j equals to 0. So if there is no point, you don't have any cost. Furthermore, you just look at the position of this I here. What is the position of I that makes the most sense? Here is that basically, for instance, in this figure, it's like basically we need to figure out this I value here. But nevertheless, this recursive call, because it is the optimal solution. So it should just be the mean of all the I from 1 to j minus 1 of the EIJ plus C plus OPT I minus 1. It should just be the minimum of these values. So any questions for this recursion? Yes. According to this definition, it does not have to be connected. So I guess here the example I'm drawing here is probably super nice, but in general, maybe it probably looks a little bit like this. So for instance, at least according to this definition, if I have vertex like this. So it might happen that, for instance, you have like a line like this. That actually it is a little bit disconnected, but I think at least according to this definition, it is fine. This is just like a little bit, maybe a little bit artificial model, but in general, along statistics, you have different ways of considering the data fitting problem. I guess the main point here is just like, I just want to demonstrate how this dynamic programming ideas is actually helpful for such data fitting problem. So any other questions? Okay, so I guess based on this, it is relatively straightforward that we can write an algorithm accordingly. So we consider this algorithm. So the algorithm input is going to be the n p1 until pn. And very importantly, for this segmented least square problem, we have this input c here. Basically this the penalty. So the penalty that we are going to pay. So there's c here. The penalty that we are going to pay for the number of lines here. So I guess in general, we can just think about, we consider this unwind recursion strategy that basically we build up this empty array, but actually we don't have to do this always from top down. We can actually do this bottom up. But nevertheless, for this recursion, it is very important that basically this EIJ, this cost using a single segment. This is something we probably need to compute at the beginning. So basically, we say that for j equals to 1 to n, and actually for I equals to 1 to j, we just compute the least square error EIJ for the segment Ti until Pj. So after that, we have M0 equals to 0. And actually, after having that for j from 1 to n. Let me finish writing this down. We have mj equals to the mean of I smaller than I 1 smaller than I smaller than j minus 1 of the ij plus c plus m minus 1. And finally, we are going to return the value of ml. So this is the final algorithm for this segmented least square problem. We are going to finish the discussion in the next class. So let's take a break now.